All right, good morning. Welcome to my stream. Welcome back. It's Friday, so happy Friday, everybody, for those of you who were watching it on a Friday. And what we did yesterday was we worked on the environments section, which is 8.3 and 8.4, I believe. We did some code cleanup too, and now we're ready to tackle, let's see, let me switch over, there we go. We're ready to tackle 8.5 scope, which is going to be, it looks like it's just going to be adding the ability to put things in blocks. So we'll see how that goes. Yeah, so 8.3 was environments. What was 8.4 then? 8.4 was, assignment. I just didn't, where is it? Yeah, 8.4 was assignment. And that should have been here, 8.4. That's all right. It's all good. So 8.5 is scope. Let's see. So our environment code looks like what right now? So we have it. All we have is a hash map in there, and we can define new values. We can get values, and we can assign. When I say define new values, so define new variables with values, and assign will modify an existing value or throw an error if it's not assigned. So we can actually cargo run. And if I say a equals 4 without defining the variable, it's going to say undefined variable. We need to clean up the error messaging. But if I can say var a and then a equals 5 or 6, I guess, print a, and it prints out 6. So this is defining the variable. It sets it to nil. If I say var b and then say print b, it prints nil. I can also say var c equals 12. So defining the variable and assigning it with an initializer, print C, print C semicolon, and it prints out 12. So that's the part we did yesterday. And now I'm thinking I want like debug commands where I can hit bang something and get a, because I want to be able to print out the current environment. Maybe we can just hack that in real quick. Because I'd like to see what the current environment looks like. And this is what run does. So I'm going to say if source equals bang, just for now. Then I'm going to say println of the current environment. Oh. And then don't do anything else. So self interpreter environment. And that probably means we need to make that pub just for that. Or we could just return the environment. We can have a something that returns that environment stuff. Let's do that. So an interpreter, simple. I'm going a little off the reservation here, but that's okay. Pub fun environment. Self returns an environment. So this is just self environment. Wait, what's the type of it? It's a ref cell. So we can just say borrow, right? Is that going to check? It does not. Found environment, found struct ref. How do we, and I don't want to do that because that'll complain about moving things. Oh wait, it worked. Okay. I thought it would complain about copy trait, but okay. So environment doesn't have debug output. I mean, derive. Debug. No, we still have an error. Yeah, move occurs. I don't want to move it. Maybe I can return this. Nope. Can I do that? Of course not. Temporary value created here. Oh, maybe I can clone it out. Nope. Can I borrow clone? Can I go as ref? Nope. I can't do any of those. I'll just say print environment. There you go. That's the easy way to do it. Println self environment. And don't return anything, and then change main to just call that function. There. Oh, and then we want this to return. We don't want to actually do anything with the input. Return OK. There. Okay, so now if I say cargo run, I can say bang, and it prints out that we don't have any environment. I can say a equals 4, and it complains. I can say var a equals 4, and then bang. And now we have a variable a with the number 4. I should be able to say b equals hello. Oh, var b equals hello. And then bang. And so now we have a b, hello, and an a. Okay. So that's kind of neat. That works out pretty well. I don't think... Oh, we do use bang in the language, so maybe bang is the wrong character for that. Because bang means not in Locke's language. So let me change it to an @ sign, because @ sign is not used. There. Okay. One more I want to think. No, that's good. That's good. Okay, so git status, git add source, git commit, debugging hack to print out current environment in the REPL. It only works in the REPL. That's fine. All right, that's that. Let's dig into scope. So a scope defines a region where a name maps to a certain entity. Multiple scopes enable the same name to refer to different things in different contexts. In my house, Bob usually refers to me, but maybe in your town you know a different Bob. Same name, but different dudes based on where you say it. Lexical scope, or the less commonly heard static scope, is a specific style of scoping where the text of the program itself shows where the scope begins and ends. In Locke's, as in most modern languages, variables are lexically scoped. When you see an expression that uses some variable, you can figure out what variable declaration it refers to just by statically reading the code. Right. Lexical comes from the Greek lexikos, which means related to words. When we use it in programming language, it usually means a thing you can figure out from source code itself without having to execute anything. Lexical scope came onto the scene with ALGOL. Earlier languages were often dynamically scoped. Computer scientists back then believed dynamic scope was faster to execute. Today, thanks to early scheme hackers, we know that isn't true. If anything, it's the opposite. Dynamic scope for variable lives on in some corners. Emacs Lisp defaults to dynamic scope for variables. The binding macro enclosure provides it. The widely disliked with statement in JavaScript turns properties on an object into dynamically scoped variables. Okay. So here we have two blocks with variable a declared in each of them. You and I can tell just by looking at the code that the use of the a in the first print statement refers to the first a, and the second one refers to the second. This is in contrast to dynamic scope, where you don't know what a name refers to until you execute the code. Locks doesn't have dynamically scoped variables, but methods and fields and objects are dynamically scoped. When play calls thing.play, we don't know if we're about to hear Careless Whisper or for. It all depends on whether you pass a saxophone or a golf club to the function. And we don't know that until runtime. Scope and environments are close cousins. The former is the theoretical concept. The latter is the machinery that implements it. So we did environments already, so now we're just going to add scope. As our interpreter works its way through code, syntax tree nodes that affect scope will change the environment. In a C syntax like Locke's, scope is controlled by curly brace blocks. That's why we call it block scope. So that's in a block. A is scoped within the block. Once the block ends, A no longer exists. The beginning of the block introduces a new local scope, and that scope ends when the execution passes the closing close brace. Any variable declared inside the block Any variables declared inside the block disappear, right? All right, then we get to nesting and shadowing. A first cut of implementing block scope might work like this. As we visit each statement inside the block, keep track of any variables declared. After the last statement is executed, tell the environment to delete all of those variables. That would work for the previous example, but remember, one motivation for local scope is encapsulation. A block of code in one corner of the program shouldn't interfere with some other block. Check this out. So we have variable volume initialized to 11, then set to 0, and then in here, in a sub block, we have a new variable volume and we print it. Look at the block where we calculate the volume of the cuboid using a local declaration of volume. After the block exits, the interpreter will delete the global volume variable. That ain't right. When we exit the block, we should remove any variables declared inside the block. But if there's a variable with the same name declared outside of the block, that's a different variable. It shouldn't get touched. All right. When a local variable has the same name in an enclosing scope, it shadows the outer one. Code inside the block can't see it anymore, and it's hidden in the shadow cast by the inner one, but it's still there. Yeah, so Rust has shadowing without having to create a block. And that's something that gets pointed out every so often. When we enter a new block scope, we need to preserve variables defined in outer scopes so they are still around when we exit the inner block. We do that by defining a fresh environment for each block containing only the variables defined in that scope. When we exit the block, we discard its environment and restore the previous one. So we have a global scope. All right. I mean, I understand what they're saying. I'm just trying to grok the descriptions here. We also need to handle enclosing variables that are not shadowed, right? Here, global lives in the outer global environment, and locals defined inside the block's environment. In that print statement, both of those variables are in scope. In order to find them, the interpreter must search not only the current innermost environment, but also any enclosing ones. Right, so when we have global, we're in this local scope, but we need to go up a level to find the global variable. We implement this by chaining the environments together. Each environment has a reference to the environment of the immediately enclosing scope. When we look up a variable, we walk that chain from innermost out until we find the variable. Starting at the inner scope is how we make local variables shadow outer ones. While the interpreter is running, the environments form a linear list of objects, but consider a full set of environments created during the entire execution. An outer scope may have multiple blocks nested within it, and each will point to the outer one, giving a tree-like structure, though only one path through the tree exists at a time. Boring name for this is a parent pointer tree, but I much prefer the evocative cactus stack. Okay. I like cactus stack. Before we add block syntax to the grammar, we'll beef up our environment class with support for this nesting. First, we'll give each environment a reference to its enclosing one. All right, so we can't do quite that, right? In Rust, we have to actually, right? Because if we create enclosing, it could be null. As we can see here, this field needs to be initialized, so we'll add a couple of constructors. We have a constructor here. We cannot, in Rust, we cannot do a method overloading. So I can't create another new method here, pubfun new with environment. This will not work. But we could just give it a different name, right? We could say new with enclosing, I guess. But what type is enclosing, right? It's got to be able to be null, which means it's got to be an option. And we can't just stick environment in here, right? Because then we have an infinite type size. And then right, I'm going to try to compile it, and it's going to complain about infinite size, right? Recursive type environment has infinite size. So the most obvious way, I guess, to do this is with a box. Oh, some, right. So that compiles. I don't know if it's going to actually work. But this is the first step. Let's see how far we get with this. The no argument constructor is for the global scopes environment, right? That's this guy here, which ends the chain. The other constructor creates a new local scope nested inside the given outer one. We don't have to touch the define method. A new variable is always declared in the current innermost scope. Oh, the define method here, yeah. So it's always going to be self-values insert. But variable lookup and assignment work with existing variables, and they need to walk the chain to find them. So here's lookup. All right, so let's write a test. How are we going to write this test? Bang test, not bang, hash test. Okay, fn can enclose and environment. So first we need let e equals environment new, and then let f, I guess, equals environment new with enclosing e. And what do we assert then? We assert that e f dot enclosing dot it's a sum, so we have to unwrap it, is equal to e. No, that won't work because this is boxed up now. Oh, and this is probably moved, so it's going to complain about the move. Oops, environment. Yeah, binary equals cannot be applied to environment. Expected struct box found environment. I guess we've already, yeah, that's the thing. We've already moved it here, I think. Oh, must implement standard partial equals. Maybe we can just say unwrap.values is equal to e.values. Can we compare hash maps like that? Yeah, here's the move. Okay, so we moved E into F, which means we no longer have access to F. I mean, is no longer have access to E anymore. I guess what we could do instead of boxing it, do a reference count on it, and that way we can clone it. Oh, expected environment. Oh, yeah. Oh, I can't. Yeah, we don't want to do reference. No, that's no good. Because if I stick a reference in here, then we're gonna. Oh, right. Well, the way to do this with the ref cell. So RC new ref cell new. This is getting messy. Oh, we need ref cell. Oops. Use standard cell. Two colons. Okay, so that worked. What we need to do then is, well, what about the test? Expected struct environment. Yeah, so we can do that now. And that's an unknown field because we need to borrow it, right? Value borrowed after move. So this is still moving. Oh. So should we pass that in as a ref cell? RC ref cell. And then down here, we have to do that. Nope. It still moved. Okay, so what if we create it that way? RC new ref cell new. And then we can say RC clone E. Nope. Expected reference found struct RC. Oh, okay, yeah. So that way we can do the reference. Oh, I missed chat. I'm sorry. Shiloh, hello. My day's going great so far. It just started though. And Zeta numbers. You were just typing new within closing? Yep. Yeah, sorry I missed the chat. I didn't have it popped out like I normally do. This is unknown field, which means we have to do a borrow here, right? There we go. So those tests worked. Okay, so this is funky because now our environment has to have this signature. And that's not what's in our interpreter. Right, our interpreter is a ref cell environment. We have to modify this to be an RC ref cell environment now in order to use this enclosing stuff. But what we need to do is actually test this. So we want to test being able to get a variable from an enclosed environment. Can move read from enclosed environment. So if we create a new environment, right? So E is our environment, and we can say E dot borrow mute define. And how do we do defines? Let's look for a define up here. Here we go. We did 3, 4, let's do 5. And let's make it a number. 77.8. Sounds like a good number. And now, oops. And now what we need to do is enclose it here in F. And then we want to insert equals after we've defined it. We want to be able to do this with F though. F dot get 5 should be 77.8, right? And this should fail because we haven't written the code to do it yet. So let's see what happens. Oh, right. I have to pass in a token. So which means I have to create a token. Let's copy those 2 lines. This will be 5. There we go. And then so this is going to become 5.get token. Okay, let's try that. Nope. Oh, like that. Yeah. So undefined variable 5, which is good, right? Because what we're doing now is seeing that we're trying to read the 5 and it should be in there, but it's missing because we didn't implement this one line here. So let's implement this one line here. It's in get. So the way we did it here is if we were able to get the object, then we clone it out. So this is going to be else if let sum enclosing is equal to self enclosing. Then we have the enclosing, we say enclosing, the same exact line, enclosing dot get name. And that will return either the object or the locks error, depending on what happens next. I didn't like that. Oh, wait, I have to say borrow. And this needs to be an ampersand. Oh, okay, that builds. Let's see if it tests. Yes, okay, so we have this part written now. If the variable isn't found in this environment, we simply try the enclosing one. That in turn does the same thing recursively, so this will ultimately walk the entire chain. If we reach an environment with no enclosing one and still don't find the variable, then we give up and report an error as before. It's likely faster to iteratively walk the chain, but I think recursive solution is prettier. Okay, we'll do something much faster in CLOCs. Assignment works the same way. Okay, so let's look at assignment. Let's create a new test. And we're going to call it canAssign to enclosed environment. So we're still going to define 5, but we want to figure out how to assign. For assignment, we need to do the tokens. So I should be able to say assert, just like I'm just looking at this line here for how to do it. F.assign 5 underscore toke and object num. It was 77.8, so now it's going to be 91.2. I don't know why I'm always picking 2 digits dot 1 digit, but that's what I'm doing. Okay, and then we need to assert that it's equal to 91.2 when we try to read it. Okay, let's run that test. That should fail. Oh, expected 2 arguments. Oh, because I put a thing there instead of where it belongs. Okay. Cannot apply unary operator bang. What? Can't I do asserts? Oh, I have to say is okay. Right, is okay. Ooh, cannot borrow as mutable. Oh, so F has to be a mutable reference here? There we go. Okay, and so that's good. F_assign panicked because it didn't exist, right? In undefined variable 5, right? So now we have to write our assign code. And I think it's the same as what we did before, else if let sum enclosing is equal to self.enclosing. Then we're going to just say enclosing assign name value. Oh, it's enclosing borrow. Mut assign name value. That checks. Let's run the tests. Ooh, okay, that all worked. This is good. This is good. Okay, let's commit these changes because these are all the environment changes, because it looks like the next part is going to be in our interpreter. So assignment works the same way. Again, if the variable isn't in this environment, it checks the outer one recursively. Okay, so what we're going to need to do now section 8.5.1 updated environment to allow enclosing. Okay, that's that. So block syntax and semantics. Now that environments nest, we're ready to add blocks to the language. Behold the grammar. Yeah, it's just curly brace declaration any number of declarations, and then closing curly brace. A block is a possibly empty series of statements or declarations surrounded by curly braces. A block itself is a statement and can appear anywhere a statement is allowed. The syntax tree node looks like this, and then we have the generated code in Appendix A we don't need to worry about. So let's take a look here. This comes down here. Block is just a vec of, whoops, that should be a colon there. Vec of statements. We're just creating statements of a vector of statements called statements. All right, and if I try to build this, we should get a failure in the interpreter saying we didn't implement visit block statement. So let's just quickly throw one in here just to stub it out. And that way we can make sure that all of our, all the other stuff is working, or compiling at least. So it just returns okay. There we go. Yes, okay. We have 3 warnings, but I'm sure those are unused something or others. As always, don't forget to run generate.ast.java. Yeah, I do that automatically as part of my build, which is nice. It contains a list of statements that are inside the block. Parsing is straightforward. Like other statements, we detect the beginning of the block by its leading token, in this case the open curly. In the statement method, we add this. Okay, let's go to the statement method in Parser. Which is right here. So we have if match print, return print statement. So now we're just going to add if self is match token type left brace return new statement block. So return statement block statement, and it just takes a vector of statements, which is, we're calling this new method here called block. So self block question mark, right? And then all the real work happens here. Okay, so private list statement block. So they're saying put it after expression statement. Sure. It's just called block. It takes a mut self and it returns a result of statement. Oh no, it returns a result of vec of statement or a locks error. We declare one up front, statements equals back new, and then we have a while loop here. While not check right brace and not is at end. Okay, so that's pretty straightforward, right? While not self check token type right brace and not self is at end. Then we're going to say statements.push self declaration question mark semicolon, and then we consume self consume token type right brace. So we check to see that we're not in the right brace and we keep doing it. As soon as we hit the right brace, we need to consume it. Okay, that makes sense. And then expect right brace after block. And then we return OK statements. Is that good? Does that look good? We create an empty list and then parse statements and add them to the list until we reach the end of the block. Let's see if that builds. Of course it doesn't. Expected underscore because of the return type. Oh, this needs to be okay. Okay, that builds. Good. Right, we create an empty list and parse statements and add them to the list until we reach the block marked by the closing brace. Note that the loop also has an explicit check for is at end. We have to be careful to avoid infinite loops even when parsing invalid code. If the user forgets a closing brace, the parser needs to not get stuck. Having block return a raw list of statements and leaving its statement to wrap it list in the statement block looks a little odd. I did it that way because we'll reuse block later for parsing function bodies, and we don't want that body wrapped in a statement block. Oh, okay. Fair enough. Yeah, we could have just put the code here. It would have been nice to do that and then done a quote refactor stage for the function bodies, right? But okay, that's it for syntax. For semantics, we'll add another visit method to the interpreter, right? So that's where we need to go here and work on this stub. So visit block statement calls execute block. So the interpreter we've been writing tests for. The parser and the scanner we have not been writing tests for. So we should probably dig in and write some tests, right? How do we test this, that we're going to call execute block and then the block gets executed? I don't know. I'm stuck. I don't know how to test this particular thing. I guess, you know, we can create a block statement and then call visit block statement and then check to see that they were executed by looking in the environment to see if the environment got modified correctly. But we have this situation here where we're creating sub-environments and none of that's gonna, and I guess it's true, I don't think I'm testing execute, am I? No. E-X-E-C-U-T-E. No. So, do we punt on testing this? I guess for now we'll punt on testing it, and if that causes issues later, we can always write a test for it once we realize what the bug is. All right. So this should be easy enough. Self-execute block. And I'll change this and then say statement dot block. Oh, statements. And then we have to create a new environment within closing, right? So environment new with, what did I call it? New within closing, I think. New within closing. Oh, right, and then we have to say RC new, right? Because we're passing an RC ref cell self environment. And this, I don't know. This is going to give us probably just as many headaches as before. Let me stub out execute block. We have execute, so let's put it right next to execute and say F execute block, which is a self, and statements, which is going to be a vec of statement. And then, oh, right, and then Clippy's going to complain. And I'm going to complain about hitting F1 all the time. And then environment, which is going to be an RC ref cell environment. Maybe a reference to it? I don't know. So let's just stub this out. This is going to return void. So this has to return result of something or locks error. And we'll just say OK for now. If I put that there, what's it going to reformat it to? 3 errors. Okay, so, oh, wait, we don't have RC. Use standard RC. RC. Still not good enough. Statements. Help a field. Oh, statements. Okay. And this has to be, I said reference, right? And it doesn't like that. Expected RC. Oh. Oh. Do I just pass in the environment then? Let's see if that works. And that has to be ampersand. And expected yeah, ref cell. Oh, not a reference to a ref cell. Oh, damn. I think I need to make this an RC ref cell as well. Which, you know, that's not the end of the world. So do that, and then I need to change the constructor, which is right here. Still one error. Expected RC frown reference. I don't want to move it though. I do want to pass in, oh, maybe I can say RC clone. There, okay. This is one of those situations where you just keep you know, hitting the hammer on the you're playing whack-a-mole basically with the compiler until you hammer things into shape. I have no idea if this works, but this is actually to the point where it compiles. Okay, with that done, should we try... Oh, we have to write execute block. We haven't written execute block yet. Okay, so let's write execute block. How is this going to work? Data number says Rust Analyzer eases the problem quite a bit. Yeah, I wish I had more Rust Analyzer going for me, but I don't know. I have it mostly turned down, and it only, you know, generates this little list of warnings and errors. Let's see what the warnings actually are. Right, yeah, that's okay, that's okay. And then what's this one? Oh, in parser, I need to consume on line 103. I need to put a question mark there. Okay. Yes. Okay. Let's go back and write execute block. So environment previous, this equals this environment. So we can't do that, right? I mean, I can write that one line of code, but we won't be able to do this part of it. How are we going to do this part of it? Right? Because this environment, I can say let previous is equal to self environment. Right? Or I can, you know, RC clone it, I guess. So, okay, I'm grabbing a pointer to it. But how do you put it back in? I can't say self environment equals previous. That's not going to fly because this is not mutable. And if I were to make this mutable, I would have to make all my visit statements mutable, which would mean changing everything. I'm trying to think now. Is there... I believe Rust ref cell replace. You can replace, just like you can borrow and borrow mute, you can do a replace. Yeah. So I can just replace 5 with 6, 6 to 5. I can replace one with the other. And it replaces the wrap value with the new one, returning the old value without deinitializing either one. So is that the way to do it? Can I say let previous? This is never going to fly, right? It's going to be self environment replace with, and it has to be the same type. So RC new ref cell new environment. And then we do it the other way around. At the end of the block, right? Execute block. Let's see if this even compiles. It does not. Of course it doesn't. Oh, it was expecting environment. It was expecting T, not RC rep cell T. So I can just throw it in that way. And okay. Whoa, no, it can't be that simple. Well, let's assume it's that simple and see what happens. All right, so this will allow us to switch this back. This will allow us to switch that back. And then for statement in statements, self-execute, statement, question mark, and then return OK. It's, oh, I mistyped this here. So this environment contains a ref to this environment. So previous should be the old environment, and self environment should be the new environment. I mean, let's see if it works. So this new method executes a list of statements in the context of a given environment. Up until now, the environment field in the interpreter always pointed to the same environment, the global one. Now that field represents the current environment. That's the environment that corresponds to the innermost scope containing the code to be executed. To execute code within a given scope, this method updates the interpreter's environment field, visits all of the statements, and then restores the previous value. As is always good practice in Java, it restores the previous environment using a finally clause. All right, well, that's okay. We're actually missing that, right? Because if this returns an error, then we're not going to replace this. So we need to actually handle this differently. I can't just question mark my way out of there. I got to say let mut error equals none, I guess. And then say if error e equals this, then we're going to say error equals e, some e, and break. And then we'll replace the previous environment, and then we're going to say if let some error equals error, and we're going to return error error. Otherwise, we'll return OK. I think that's the way around this try finally thing. If there's a better way to do it in Rust, that would be good to know. If let. There we go. Right, that way if a statement executes and it returns void or this unit value in Rust if everything works, otherwise it returns an error. We get the error here, we save it in error because this is scoped within the for statement. So we're going to put it into the outer scope by doing this, and then we'll grab it from the outer scope here and return it as a locks error, and then keep going. I think that's what this maps to. It's a little ugly, but it does the trick. I guess we could clean it up a little bit more by saying OK, and then just say error is error e, and then just return error. Can we do that? Yeah, that likes it. And instead of calling it error because it might not be an error, it might be just result. Yeah, okay. I think that's a little bit cleaner. I'm still thinking about this. We can say result is equal to self-execute statement, semicolon, if result is error, break. That way we're not destructuring it each time. Yeah? Okay, let's go with this version. Let's go with this version. Okay. To execute code within a given scope, this method updates the interpreter's environment field, visits all of the statements, and then restores the previous value. Oh yeah, we read that already. Surprisingly, that's all we need to do in order to fully support local variables. Nesting and shadowing. In addition to nesting and shadowing. Go ahead and try this out. Okay, we will. Manually changing and restoring mutable environment field feels inelegant, yeah. Another classic approach is to explicitly pass the environment as a parameter to each visit method. To change the environment, you pass a different one as you recurse down the tree. You don't have to restore the old one since the new one lives on the Java stack and is implicitly discarded when the interpreter results from the block's visit method. I consider that for JLogs, but it's kind of tedious and verbose adding an environment parameter to every single visit method. To keep the book a little simpler, I went with a mutable field. Zeta number says, couldn't you just return error E? If I return error E here, then we don't get the replace, right? We don't. Well, I want to execute this line of code before we return, and I could put it up in here too, right? I could just say, you know, if let error E equals self blah blah blah, then self environment replace, and then, you know, return error E. But then we have this line of code here and here, which I don't want to do. I just want to have it in one spot, one throat to choke. There's iterator try for each to short circuit on error. Okay, that's interesting. That's very interesting. Rust, iter, try for each. How does that work? Rust stabilize, try fold, and try for each. That was 2018. Okay. Try for each. An iterator method that applies a failable function to each item in the iterator, stopping at the first error and returning that error. This can also be thought of as a failable form for each. And if everything's okay, what does it return? Is okay. Huh. Okay. I'm liking this. Statements, try for each statement. Self execute statement. Like this? So it'll stop at the first error, which is what we want. All right, well, let's give it a shot. I mean, I like it. Try for each is not found in statements. Iter. Okay, let's give it a shot. I like this. It's nice and compact, and it does exactly what we were trying to do in one line of code. Well, 3 lines now, but you know what I mean. Yeah, nice. Thank you, Zeta numbers. Go ahead and try this out. Okay, let's go ahead and try this out. Let's call it, I don't know, block.locks. No, it doesn't allow me to triple click. One of the things that's nice about Advent of Code is when they have code blocks like this, you can triple click and get the whole block. Eric was very kind to be able to do that, to provide that. So, okay, here we go. Boom, boom. Cargo. This all checks, right? Yeah, cargo, run, lock, locks. All right. That's not quite what I was expecting. Okay, so we have some sort of weird overflow going on here, which means we have infinite recursion somewhere along the way. Let's figure that out. But first, I just want to figure out what's the output going to be of this thing. All right, we're printing A, which is inner A. We saw that. It was as soon as we tried to go to outer scope that we hit the infinite loop. Oh my God, are we seriously still doing spams? Okay, hang on, I just need to mod these guys out of here. Which I don't know how to do off the top of my head. Block. They're getting cleverer now with the different. Here we go, and block. And how do I delete those messages? I don't know how to delete those messages. Ban. And let's try again. Ban. Good. Okay. I think I figured it out. Sorry about that. Sorry for the distraction. I was trying to figure out what the output should look like. Right? And I think it should be like, we have inner A, which is right. So we got that far. It should print for B, outer B. And for C, it should print global C. Right? So it should say inner A, outer B, global C. Then at this level, it should say outer A, outer B, global C. And this level should be 3 globals. All right. So let's figure out what's going on here. And it's obviously in this execute block when we're trying to do these things. Maybe the replace is not working right. Let's find out. So if I say println here of self environment, this is where it's handy that I actually did the thing here. So I should be able to say current environment is equal to this. And then there we go. Previous env is equal to, let's see what we captured out of there. And then we're going to say replacing with environment. So we should be able to see what's going on as we go through these steps here, right? And then we'll do this thing, and then we can just say println restoring self environment. Okay. Is that enough debugging? I don't know. I hope so. All right, let's see what happens now if I run this. Cargo run block locks, and I'm gonna pipe it into less. Ooh. Okay, so we're still seeing this overflowed stack business. What's at the top of this thing here? So the current environment is this environment. It has C, A, and B, right? So that we're here. We're about to start this very first block statement. We're replacing it with something without values, but it does have the enclosing of C, A, and B. And the previous environment now is our current environment. And as soon as we do that, now we're saying current environment is equal to, and it's recursively defining value environment, values. All right, this is the ref cell. And it's just recursive now. I think what's happening, is that when we go into the next level here of execution, it must have created a loop. When we said environment new with enclosing, this must be referring back to the original one, and therefore making an infinite loop. How do we solve that problem? Let me just print that out into here. Println. Actually, we can say let e equals this line. Right, and we can say println visit block statement. New environment is equal to this e, and we can pass e here. Oh. Yeah, okay, so let's run that. Here's visit block statement. Okay, so if I just do this, oh, it's right here. So this is where we're messing up. We're getting the wrong enclosing, or the enclosing gets to be a little too much. Because this worked. The current end worked. Replacing with worked. And previous end was that. And now we called the next visit block statement recursively. And that ended up causing this problem. So this is what our environment is. And we need to create a new environment with this environment as the referent. And we're not doing that. We're ending up just creating this infinite loop here. Huh. I wonder... I think if we just add another layer of indirection, that might help. Because then we'll have an extra ref cell in the way. Is what I'm thinking. It should jobs. Yeah. This is what I'm thinking. Is if I make this a ref cell, then we can borrow instead of. Right, then we'd be able to just borrow this here. And would that avoid the loop? Right, we can clone and borrow. And then, okay, we're gonna have to change all these things here. I'm gonna need double. Oh, I messed something up. Yeah, so because we want the RC, right? We want the environment. We don't want this. This is expected RC found struct ref. So maybe it's borrow clone. Yeah, and then all these need to be borrow. Here and here. Double borrows. I'm struggling here. This needs ref cell new. And then this needs to change. Because now we have the environment. Now we need to replace it with an RC. Yeah. And maybe that level of indirection will help us. Yes, it does. Okay. That's the so just as a lesson learned, this is typically the way you solve problems in computer science. If you're having issues, just add another layer of indirection. But I think, so we're seeing it here, right? Inner A, which is what we were expecting, then outer B, which is what we're expecting here, and then global C, right? And then outer A, outer B, global C, which is what we expect here, and then global A, global B, global C. So that works. That was a little bit of a struggle, but it worked. Now we have to clean up all of our debugging output, which is just all the printlns. Oh, this one we need because that's the actual print statement. So that's those. And that's print environment, which is fine. That checks. Cargo, run, block. Boom. Okay, so we're good. We're good. We finished this. Git diff. What did we do? We added block statements. We added this extra level of indirection. We're now borrowing everywhere, so we have these double borrows, unfortunately, but you know, that's the price you pay. What else? This is this. Here's our execute block, and I want to thank Zeta Numbers again for this really cool one-liner. And this is the parsing of the block statements, and this is how we assemble the block statements. And we're done. Okay, so this was section 8.5.2. Section 8.5.2, block statements. And scope. Yeah, okay, that's good. That's good. And I have about a little over a half hour left. Let's see, let's take a look at the challenges. The REPL no longer supports entering a single expression and automatically printing its result value. That's a drag. Add support to the REPL to let users type in both statements and expressions. If they enter a statement, execute it. If they enter an expression, evaluate it and display the result value. Maybe you want locks to be a little more explicit about variable initializations. Well, okay, yeah, I'm not going to do this though. Instead of implicitly initializing variables to nil, make it runtime error to access a variable that has not been initialized or assigned to. Oh, I see. Yeah, so right now I can say cargo run and say var A and then print A, and it prints up nil, but this is saying make that an error. And we could do that. That's straightforward. What does the following program do? Var A equals 1, var A equals A plus 2, print A. I'm going to guess that this A gets from this scope. So this is going to be 1 plus 2. It's going to get 3 here, and this is going to print 3. But if I said print A down here, it would print 1. Let's try it. What do I want to call it? Scope. Blocks. Var A equals 1. Scope. Var A equals A plus 2. Print A. Close scope. Print A. So I'm going to guess the first print is going to print 3, and the second print is going to print 1. That's my guess. Yeah, that works. What did you expect it to do? Is that what you think it should do? What does the analogous code in other languages you are familiar with do? What do you think users will expect this to do? I don't have any of the answers to any of those questions. Locks has distinct syntax for declaring a new variable and assigning to an existing one. Some languages collapse those into only assignment syntax. Right. Implicit declaration has problems, but it makes it more friendly, I guess, to users. I prefer explicitly declaring variables, which is why locks requires it. Okay, good. I think we're good. Status. We can work on the next chapter, control flow. Oh, we're up to chapter 9 already. Compared to last chapter's grueling marathon. Was it grueling? Today is a light-hearted frolic through a daisy meadow. But while the work is easy, the reward is surprisingly large. Right now, our interpreter is little more than a calculator. A LOX program can only do a fixed amount of work before completing. To make it run twice as long, you have to make the source code twice as lengthy. We're about to fix that. In this chapter, our interpreter takes a big step towards a programming language, major leagues, Turing completeness. All right, so Turing machines. In the early part of the last century, mathematicians stumbled into a series of confusing paradoxes that led them to doubt the stability of the foundation they had built their work upon. That's a sentence. To address that crisis, they went back to square one. What is this crisis which we are linking here? The crisis is the foundational crisis of mathematics. Okay, I will read that later. Starting from a handful of axioms, logic, and set theory, they hope to rebuild mathematics on top of an impervious foundation. Most famous is Russell's paradox. Initially, a set theory allowed you to define any sort of set. If you could describe it in English, it was valid. Naturally, given mathematicians' predilection for self-reference, sets can contain other sets. So Russell, rascal that he was, came up with R as a set of all sets do not contain themselves. Right. Does R contain itself? If it doesn't, then according to the second half of the definition, it should. But if it does, then it no longer meets the definition. Cue mind exploding. Right. So there's Turing completeness. I'm not going to go through all of Turing complete stuff. We will skip forward to conditional execution. Because I know what Turing completeness is, and it's easy enough to look up. Enough history. Let's jazz up our language. We can divide control flow roughly into two kinds. Conditional branching flow is used to not execute some piece of code. Imperatively, you can think of it as jumping ahead over a region of code. And then looping control flow executes a chunk of code more than once. It jumps back so that you can do something again. Since you don't usually want infinite loops, it typically has some conditional logic to know when to stop looping as well. Branching is simpler, so we'll start there. C-derived languages have two main conditional execution features, the if statement and the something named perspicaciously, having ready insight into the understanding of things. Okay? Conditional operator, this. Right. An if statement lets you conditionally execute statements, and the conditional operator lets you conditionally execute expressions. The conditional operator is also called a ternary operator because it's the only operator in C that takes 3 operands. For simplicity's sake, LOX doesn't have a conditional operator. Okay, good. So let's get our if statement on. Our grammar looks like this. Semicolons in the rules aren't quoted, which means they are part of the grammar meta syntax, not LOX's syntax. A block does not have a semicolon at the end, and an if statement doesn't either, unless the then or the else statement happens to be the one that ends a semicolon. All right, so we're going to add our if statement. An if statement has an expression for the condition. Epic Blog said, I thought I learned a new word, but then I already forgot it. Almost perspiration? Almost perspiration? Is that the perspicacious? I don't know how to pronounce that. I'm sorry. It had it, the definition here, but I just lost it. Oh, and now I'm going to execute. Come on, there we go. Perspicacious. Perspicacious. Sure. Okay. I'm definitely perspirating through that. I was perspirating through that scope section, trying to get that to work, because I was like, uh-oh, if I can't get this to work, I'm going to be stuck here for an hour. All right, so we're going to go here. So expression, we're going to add our if statement. It's going to take an expert condition, a statement. Oh, it has to be boxed though, because we're in statement. We need to box it up, a then branch, and then a box statement for the else branch. Okay. Like other statements, a parser recognizes an if statement by the leading if keyword. All right, so we'll add that. We should be able to do this, and when we get a warning or an error in here, so I'm just going to stub this out for now. Visit if statement. I'm just going to say okay. Good. Okay. So in our parser, we're going to modify a statement, which is right here. So we check print. Oh, we checked this before we check print. If self is match. I'm not sure it matters, but it's okay. We'll be consistent with the book. If it's an if, then we're going to return a self if statement. Okay. When it finds one, it calls this new method to parse the text. So let's implement that. We're going to add it right after statement, they say. Okay. Epic Blog says, how goes the interpreter crafting? Have you managed to map everything to Rust so far? So far, yes. So far, we're good. We're in chapter 9. How many chapters are there? Unfortunately, this is not wide enough to show the table of contents on the left, but we can go up here real quick. How close are we to completing? Oh, okay, so we're just over halfway through. We finished 8. We're halfway through this. We're going to get to functions, resolving binding, classes, and inheritance soon. And then after that, we're going to do C-locks. But next week, before we do all of that, we're going to go back to the roguelike tutorial and have fun with that. And now I lost my place. Oh no. Here we go. So we're going to start by consuming token type left paren. And it says expect left paren after if. And then we're going to say let condition is equal to self expression. That's one of the neat things about this code, is allowing me to a lot of self expression here. Okay, so we have this line here, and then we're going to expect a right paren. Like that. Let's put those 3 lines together, and then we have the statement. Then branch is equal to self statement. And then, oh, question mark, right? And then else branch, let else branch equal if self is match token type colon else. If it is, then we're going to create a statement, self statement, question mark. Else it's going to be none. Oh, right. So this has to be a sum, and this has to be a none, and that means we have to go back to our parser generator and modify this to be an option. Okay, and then this will just return a new statement. So this is going to be an OK of a statement if, which is if statement, which is going to take in condition, a then branch, and else branch. And I think I need to box the then branch up. So let's do that. Box new. There's that. And then we need to box these guys too. We need to box this. We don't need to box up the none. Okay, that. Let's see if this compiles. It does. We got 3 warnings. Okay. Because we're not using them. All right. The parentheses around the condition are only half useful. You need some kind of delimiter between the condition and the then statement, otherwise the parser can't tell when it has reached the end of the condition expression. But the opening parentheses after the if doesn't do anything useful. Dennis Ritchie put it there so we could use close brace as the ending delimiter without having unbalanced parentheses. Yeah, and in Rust, the way they do it is you always have to have an opening brace on the line after the if. So that's how you know your condition is done, is when you hit this thing here. Whereas in C, that's optional if you only have one statement. Oops, sorry, I just hit my mic. Hopefully that wasn't too loud. Okay. So, right, other languages like Lua and some basics use a keyword like then as the ending delimiter and don't have anything before the condition. Go in Swift instead require a statement to be a brace block. Yeah, go Swift in Rust. Okay. As usual, the parsing code hews closely to the grammar. It detects an else clause by looking for the preceding else keyword. If there isn't one, the else branch field in the syntax tree is null, or in our case, is none. That seemingly innocuous optional else has in fact opened up an ambiguity in our grammar. Consider this: if first, if second, when true, else when false. Here's the riddle. Which if statement does that else clause belong to? This isn't just a theoretical question about how we notate our grammar, it actually affects how the code executes. If we attach the else to the first if statement, then when false is called if first is falsy, regardless of what the second value was. If we attach it to the second if statement, then when false is only called if first is truthy and second is falsy. All right, so we can interpret it this way, or we can interpret it this way. This is a classic pitfall of a syntax called a dangling else problem. It is possible to define a context-free grammar that avoids the ambiguity directly, but it requires splitting most of the statement rules into pairs, one that allows an else with an if and one that doesn't. It's annoying. Okay, instead, most languages and parsers avoid the problem in an ad hoc way. No matter what hack they use to get themselves out of trouble, they always choose the same interpretation. The else is bound to the nearest if. Our parser conveniently does that already. Since if statement eagerly looks for an else before returning, the innermost call to nested series will claim the else clause for itself before returning to the outer if statements. Syntax in hand, we are ready to interpret this. Okay, so let's go back to our interpreter. And we can visit the if statement. So if is truthy, we do have the is truthy, right? We wrote that a while ago. Yeah, right there. Okay. Self is truthy. Self evaluate. Statement condition question mark. Then we're going to self execute statement, then branch, and we'll return that result else if let sum else branch equals statement else branch. Oh, in the past we've been putting ampersands in front of these, so I'm just going to do that without understanding why. Then we're going to say self execute else branch, and I think this one doesn't need the ampersand because we just had it here. I guess. Else, okay. Is that it? Nope, that's not it. Oh, I forgot to take the underscore out. Expected object, didn't get object. There we go. And we still have 3 warnings. What are the warnings? Oh, I forgot the consumption here. Parser. There we go. Line 72 should be question marked, and line 74 should be question marked. Okay. So that should clean up those warnings. Yes, it does. The interpreter implementation is a thin wrapper around the self-same Java code. It evaluates the condition. If truthy, it executes the then branch. Otherwise, if there's an else branch, it executes that. If you compare this code to how the interpreter handles the other syntax we've implemented, the part that makes control flow special is that Java if statement. Most other syntax trees always evaluate their subtrees. Here, we may not evaluate the then or else statement. If either of those has a side effect, the choice not to evaluate becomes user visible. Yeah. So if we look at the other statements, right, we just execute the print, we execute the evaluate, execute the block. Here, we are executing the initializer optionally, so it is kind of the same, but this is more directly if true, then else, right? Okay, so we did this. We've gotten the if statement done. It would be nice to have a little a quick little test before we commit these changes. Cargo run. If open paren 4 equals 5, open block, print yes, semicolon, else. I have to do it all on one line because we currently don't have a REPL that can do multi-line input. Maybe that's something we can add. No. And then we can say if 5 equals 5. And we can just copy paste this. The other thing that would be nice in the REPL is having up arrow work. But that's not going to work. That just gives me escape open bracket A. Okay, so this works, right? We got this 4 equals 5, blah, blah, blah. We should also be able to do it without an else clause. For false and without an else clause for true. There you go. So that all works. Git. It is. Yeah. Let's do a clippy. Good. So git add, generate, and then source. Git commit. Section 9.2 if statements. All right, so now we're up to logical operators. Since we don't have the conditional operator, you might think we're done with branching, but no. Even without the ternary operator, there are two other operators that are technically control flow constructs, the logical operators and to or. All right, I don't know if I'll have time to get into this. How long is this chapter? Yeah. Well, let's see how far we can get. And we might have to just finish up tomorrow. These aren't like other binary operators because they short circuit. If after evaluating left operand we know what the results of the logical expression must be, we don't evaluate the right operand, for example, false and side effect. For an AND expression to evaluate to something truthy, both operands must be truthy. We can see as soon as we evaluate left false operand that it isn't going to be the case, so there's no need to evaluate side effect, and it gets skipped. This is why we didn't implement the logical operators with the other binary operators. Now we're ready. The two new operators are low in the precedence table, similar to OR and in C. They each have their own precedence with OR lower than AND. We'll slot them right between assignment and equality. I've always wondered why they don't have the same precedence, like the various comparison and equality operators do. I think because AND is kind of similar to multiply and OR is kind of similar to add, maybe? Instead of falling back to equality, assignment now cascades to logic OR. The two new rules, logic OR and logic AND, are similar to other binary operators. Then logic AND calls out to equality for its operands, and we chain back to the rest of the expression rules. Okay. The syntax doesn't care that they are short-circuited. That's a semantic concern. Right, okay. We could reuse the existing expert binary class for these two new expressions since they have the same fields, but then visit binary expert would have to check to see if the operator is one of the logical operators and use a different code path to handle the short-circuiting. I think it's cleaner to define a new class for these operators so that they get their own visit method. All right. So literal comes right after here. Well, logical. It's going to be expert. Oh, sorry. Box expert. Left. Token. Operator. And box expert. Right. So, like he said, they're exactly the same as binary, but we're going to have a separate class because reasons. To weave the new expressions into the parser, we first change the parsing code for assignment to call OR. Is that going to work in... I don't know if I can create a function called OR or AND, because there's one AND I see here down. Let's stub out the visit logical. Okay, object nil. And that way we get it to build. Okay, and now we're going to go back to the parser. And in assignment, we're going to call OR. It might work. I don't know if it's a reserved word. Like do is a reserved word. If I type do, it gets highlighted in red because it's a reserved word even though it's not used. So let's find out. So instead of calling quality, we're going to call or here. Oh, it didn't complain. All right, so far so good. So after assignment, we're going to write our or. And it returns an expression. And it calls and. Okay. Self and. Question mark. Right? And then while match or. That's, yeah, so we're in or, we're saying while there's an or going on, then let operator equals self previous. Right, this is going to be similar to the equality thing, right? So we're just going to copy this. I'll put the dupe in there. Oops. Like they have here, and this probably needs to be mut. Because we have to say let right is equal to self and question mark, and then expr is equal to expr logical expr brace of expr left is going to be a box new of expr. The operator is going to be operator, and then right is going to be a box. I guess we can just put the box here. Just to make things a little cleaner. And then here we just say OK expr. And then we have to write and. And and is exactly the same thing, except we're going to call equality. 1, 2, 3. So 3, Y, grab, paste. And this will be and this will be equality. And this will be equality, right? It's the same exact thing otherwise. Yes. That works for me. Okay, so maybe we're going to get this done after all. And let's see, does this build? It does, wow. This calls equality for its operands, and with that, the expression parsers are all tied back together again, and we're ready to interpret. Okay, so now we have to go back to the interpreter. And we're going to write this. So object left is self evaluate expr.left. Oop. Gotta remember to do that. Question mark. If. Oh, right. We want to be able to match token type. So expr.operator. I think I have an is. I think I have an is function somewhere. And then if, this is interesting, self is truthy of left, then we're going to return OK of left. Else, if not self is truthy of left, we're going to return left. I guess we should do it. We need to have a return statement here because there's no else clause there. Return left. And then otherwise we're going to return self evaluate expr right. Is that it? No, it's not it. That's it. Okay. If you compare this to the earlier chapter's visit binary expression method, you can see the difference. Here we evaluate the left operand first. We look at its value to see if we can short circuit. If not, and only then, do we evaluate the right operand. The other interesting piece here is that deciding what actual value to return. Since locks is dynamically typed, we allow operands of any type to use truthiness to determine what each operand represents. We apply similar reasoning to the result. Instead of promising to literally return true or false, a logic operator merely guarantees it will return a value with appropriate truthiness. Fortunately, we have values with proper truthiness right at hand, the results the operands themselves. So if we use those, for example, high or 2 prints high, nil or yes prints yes. So we can actually test that on the command line. I should write a formal test for this down in our test code here. But building something that will do this will take a little bit more brain power than I have left for the rest of the stream. So I'm going to think about that. Maybe I'll write a test for it after. So let's see. Let's try this out. Print high or 2. This should work, right? Yep. So this was the first thing that evaluated true. So that, therefore, the whole expression was going to be true. Print nil or yes. Prints yes. Because nil was false, but yes was true. And if I say print 0 or 1, it's going to print 0. If I say print 0 and 1, we have a parse error. Okay. Let's take a look. Maybe I messed up the parser code. Oh, I did. This should be and. Duh. Okay. Let's try that again. This is why you gotta write tests. But I don't have tests for my parser. Print 0 and 1. Prints 1. Because they're both true. Print false and 1. Prints false. Print true. And 1. That's 1. Right, because it evaluated true, and then it had to evaluate that. So if I say print 1 and true, it should print true. Perfect. That went very quickly. Get diff. So what did we do? We added the logical here. We added our logical visit. And then we added the code to parse the ends and the ors. Very simple, very straightforward. Okay. What does Clippy think? Oh, okay. We can fix these, I think. This one is a little different because we're going to change the view of it. This one doesn't need the question mark. Epic Blog says that's actually pretty cool. Yeah, I agree. I really like this book. Did you go through it, Epic? 71. Yeah, so we don't need the question mark there. Actually, we don't need any of that, right? Because self-evaluate already returns object or locks error. Yeah. And then here, this is what Clippy is suggesting we do. I mean, if you look at it this way, you can see the pattern pretty easily. If it's an OR and it's truthy, return the left side. Then we're done. If it's not an OR, it must be an AND. And then if it's not truthy, then we'll return the left side. Meaning false, right? So it kind of breaks it up into this is the OR side and this is the AND side. But if I put this back like this is the OR side, and I guess we can read that this is the AND side. Right? It should still work. And Clippy should be happy now. Cargo run. Print false and 1. It's false. Print true and 1 works. Print 0 or 1. Print 0. Print nil or yes. Prints yes. Okay, so that all works. Epic Blog says, I was planning to, but when you started, I decided to live vicariously through you instead. Okay, so what I'm going to do is I'm going to go all the way up to just before the last chapter, and then you got to finish it. No, I'm just kidding. I'm going to finish the whole thing. I can't stop there. All right, so we did this. So git status, git add generate and source, git commit, -m section 9.5. And these are logical operators. All right. I'm going to push on a little bit more because I want to see, I'm going to check out while loops. And I've got 10 minutes, but I might, yeah, this looks like we could do this in 10 minutes, right? While loops. And then we can save 4 loops for when I come back to this. Although next week is roguelike week, not interpreter week. So let's finish these up. While loops. Locks features 2 looping control flow statements, while and for. A while loop is the simpler one, so we'll start there. Its grammar is the same as in C. Epic says, I've been eyeing crafting interpreters for quite a while, but never got around to it, so it's good to be able to watch someone stream it. Yeah, and you know, this is all done here in Java, and that what motivated me to do it was to port it to Rust, or to try. It would help me learn how Rust works, right? Because this is supposed to be learning how to write an interpreter, and I kind of already knew all of this stuff from way back when. So it's refreshing that memory, but it's helping me learn Rust. This would be good for, like, you know, someone taking AP high school Java. This would be a really good project to work on for them, I think. It would help them learn Java and learn interpreters, which would be great for college level, university level courses. While, and this is going to take an expr of condition and a box statement for the body. Right? Epic says, do you feel like you've had to resort to ownership and cloning where you'd really like to use references? I've so far avoided dealing with lifetimes, which is great, but I don't know if you can see here at the beginning of the stream, we had to go kind of nuts in order to work around an infinite loop problem. And if we look at an environment now, we have this option RC ref cell environment for the enclosing. So I've been stretching the bounds of my knowledge in order to solve these issues. And if you look down here, we have this borrow file by borrow mute. It would be really nice to clean that up, having this double ref cell. I think if I knew more Rust, I'd be able to make this cleaner. Epic says, my gut feeling is that this would happen quite a bit when working with parsers, but I don't base it on anything other than irrational intuition. Yeah, so the parser does have a lifetime marker in it, and that was only because we were passing the tokens in from the stream, from the scanner. Instead of copying them, we're passing the reference to them, and that's where the lifetime came in, but that's pretty minimal. All of the difficult work for me has been in the interpreter side rather than in the parsing side. Okay, let's stub out visit while statement. Okay, that's that. So now we're getting it to build. In the parsing side of things, we are in statement, so after print, but before left brace, we will put this. And it's just return while statement. Okay. This delegates the real work to this method, and we're going to put it after var declaration, which is, yeah, right there. And what is this doing? This is returning a statement. All right, so we're going to do a consume of left paren. I'm sure I have that somewhere else already. Let me just copy this line and change the things around. So left paren, expect left paren after while. Okay, and then we're going to say let condition is equal to self-expression. And then we're going to consume a right paren. Like that. And then we'll say let body equals self-statement. And then return, sorry, it should be okay. Statement, while statement. And this is going to be condition and body. Oh, we have to box it. I forgot. Box new. Ooh, that checked. First try. The grammar is dead simple, and this is straight translation of it to Java. Speaking of translating straight to Java, here's how we execute it. Okay, let's go back to the interpreter. And we'll do this. While self is truthy, self evaluate, statement condition, question mark, self execute, statement body, question mark, and then return null. That was easy. Oh, oh right. There we go. Like the visit method for if, this visitor uses the corresponding Java feature, right? Corresponding Rust feature. This method isn't complex, but it makes locks much more powerful. We can finally write a program whose running time isn't strictly bound by the length of the source code. Right, so I can write an infinite loop. Cargo run. While true, print Uncle Scientist is great. Look at that. My first basic program re-implemented in locks. Okay, enough of that. So we have infinite while loops now. We should actually be able to write a var n equals 4, sure. Typo that. While n is greater than 0, print n equals n minus 1. Right? We should be able to do this. Oh, look at that. So get status, get diff. All right, so we added the while, we added the while, we added the while, and we added the while. Pretty straightforward. Clippy should be happy. That was pretty basic code, right? Yep. Oops. There we go. And that was section 9.4, while loops. And I think I am now definitely out of time. So we're going to get to for loops not next week, in 2 weeks. March 7th, March 14th is when we'll do while for loops. So let's push these changes up and call it a stream. We got a lot done. This was the tough one here. 8.5.2, getting this going was it looks very simple, very straightforward, but that took a lot of time to figure out how to get this. We had some sort of infinite loop going on in execute block where the statements were self-referential, but it all did the trick. Epic Blog cheers, and Zeta Number says, hey, okay, good. We are good. So next week we're going to start up with the roguelike tutorial, items that affect attributes, and better status effects. So I look forward to that. I look forward to seeing you next week. Have a great weekend, everybody. I had a good time. Togglebit is still streaming. If you want to go check out him, I'm not going to do a raid. And take care.